Hello everyone. Today we're going to be learning about DES, the Data Encryption Standard, which is a modern symmetric encryption algorithm. It is a block cipher method where we encrypt the plain text in blocks of data as opposed to individual bytes or bits in a stream cipher. Before we learn about DES, we need to understand what a feastal structure is. A feastal structure is used to encrypt plain text to ciphertext by using multiple feastal rounds. Each round has its own plain text and key. The unique keys at each round are generated from a master key. We will look into how key generation works later. First of all, we start off with a plain text, which is divided into two halves, L0 and R0. At the next round, the plain text will become L1 and R1. At the round after that, the plain text will become L2 and R2 and so on. To find out L and R at a given round, we can use two simple formulas. New L is equal to old R and the new R is equal to the encrypted old R XORed with the old L. For example, L1 will simply be R0 without any changes. To find R1, we first encrypt R0 with key 1 and then XOR the result with L0. This gives us R1. We can repeat the same steps for further rounds until we desire to stop. DES involves 16 feastal rounds, hence it is necessary to understand the feastal structure. Let's look at some of the key points of DES. DES is a block cipher which processes fixed size blocks simultaneously as opposed to a stream cipher which encrypts data one bit at a time. It is a symmetric cipher, which means that the same key is used for encryption as well as decryption. The plain text is divided into blocks of 64 bits each. There are 16 feastal rounds, as we saw earlier. Let's look at the steps involved in DES. Initial permutation. In the initial permutation, we scramble the original 64-bit plain text. For example, we can make the first bit the 53rd bit, the second bit becomes the 19th bit, and so on. After that, we perform 16 feastal rounds on the plain text we just generated. At the end of the 16 rounds, we swap the left and right halves of the resulting ciphertext. We then perform the inverse of the initial permutation we did in step 1. This is performed only once. The original key is 64 bits, but we converted it to a 56-bit key by discarding every 8th bit. This is known as PC1 or permuted choice 1. That key, the 56-bit key, is further changed to 48 bits by shifting. Now we will look at what happens in each of our 16 feistal rounds. As seen before, the 64-bit plaintext we received after the initial permutation is divided into two halves of 32 bits each. To get the left half of the plaintext in the next level, we simply pass the right half of our current level. To get the right half of the plaintext in the next level, we first have to pass the right half of our current level through a function along with the 48-bit key of that level. The resultant output is then XORed with the left half, and this becomes the right half for the next level. So let's look at what the function along with the 48-bit key does to the 32-bit data from the right half of the plain text. First, the 32-bit data is passed through an expansion box and is converted to 48-bit data. This resultant data is then XORed with the 48-bit key for that level. This 48-bit data is then passed into 8 substitution boxes, and the result is 32 bits of data. The substitution boxes converted the 48 bits of data to 32 bits. These 32 bits are then finally passed through a permutation box, and the final result is a 32-bit output. This 32-bit output goes on to be XORed with the left half of the plaintext and becomes the right half of the plaintext for the next level. What happens inside the expansion box? Inside the expansion box, we need to convert our 32-bit data to 48-bit data. The 32-bit data is split into 8 blocks, each of size 4 bits. We convert each 4-bit block to a 6-bit block by adding 2 bits to it. Eventually we get 8 blocks of size 6 bits each, and our result is 48-bit data. So how are these bits added? For each new block, we take the original block and append the last bit of the previous block at the beginning and the first bit of the next block at the end. For example, suppose we want to expand this box give. To do so, we copy the box as it is with the letters GIVE, and we append the last bit of the previous block, which is a T, at the beginning, and the first bit of the next block at the end, and hence we end up with a 6-bit block. We repeat this process for all the blocks from 1 to 8. For representation and understanding purposes, I've used letters here, but actually the data is only zeros and ones, not letters. Since the first block has no previous block and the last block has no next block, we wrap around and form a cycle. That means that the previous block for the first block is the last block, and the next block for the last block is the first block. If this is confusing, our first block was don't, and if we want to create don't, we append the first letter of the next block, which is a G, to its end. But what do we do about the first bit? For that, we go to the last block, which is the 8th one, and take its last bit, which is E, and append that to the beginning. Similarly, for the last block, we append the first bit of the first block to become its last bit. Now every 4-bit block has been converted to a 6-bit block. These 48 bits are now XORed with the 48-bit key and given to the S boxes. Let's look at what happens in each S box. The 8 S boxes, short for substitution box, are used to convert the 48-bit data back to 32-bit data. Since there are 48 bits of data and 8 boxes, each block receives 48 divided by 8, which is 6 bits of data, and outputs 4 bits of data. To help perform this operation, we are provided with an S table. We do not have to remember it. Suppose the 6-bit input to one of the S boxes is 001011. The middle 4 bits represent the column, while the outer 2 bits represent the row. So in this example, our row will be 01, which if we convert to decimal is 1, and our column will be 0101, which in decimal is 5. Now we check the first row and 5th column in the given S table. Suppose that the value at the first row and 5th column is 7. If we convert 7 to binary, we get 0111. This is a 4-bit data, and hence we have converted our 6-bit data, which was 001011, to a 4-bit data, 0111. We perform the same operation at all the 8 S boxes and end up with 32-bit data. Let's look at how the 16 keys K1, K2 all the way up till K16 are generated. As seen in each round, a 48-bit unique key is used. Earlier we saw that we started with an original 64-bit key, which was converted to a 56-bit key by removing every 8th bit. This process was called permuted choice 1 or PC1. But how do we get the 16-bit unique 48-bit keys from this 56-bit key? In this process too, we have 16 rounds. The 56-bit key is divided into 2 halves of 28 bits each, called C and D. In each round, we shift the bits of each half by some specific amount. This shifted data is then passed on to PC2 or permuted choice 2, which gives the 48-bit key as the output. This process is repeated 16 times and 16 unique keys are generated. The number of shifts we perform in each half depends on which round we're at. In rounds 1, 2, 9 and 16, the shift is rotating left by 1 bit. But in the other rounds, the shift is rotating both halves left by 2 bits. You must also be curious as to how PC2 generated a 48-bit key from 56 bits. It does so by choosing 4 bits from C, 4 bits from D, and then discards them. Hence total 8 bits are removed and we are left with a 48-bit key. These 8 bits are chosen based on a predefined table. Let's take a look at what we've seen so far. First we studied the Feistel structure and saw how the plain text is divided into two halves, passed through multiple Feistel rounds, and how we ended up with the ciphertext. We then looked at the major steps involved in DS. The first step was to perform the initial permutation and rearrange the bits of the original 64-bit plaintext. In the second step, we looked at the entire working of the 16 Feistel rounds. Each round involved a unique 48-bit key and a function. Inside the function, the 32-bit data from the right half of the plaintext was converted to 48-bit data through the expansion box. This resultant data was XORed with the 48-bit key and then passed on to the substitution boxes, which converted it back to 32-bit data. This 32-bit data was put through a permutation box, and we finally got our 32-bit output, which would go on to be XORed with the left half of the plaintext. We also looked at how the 16 48-bit keys were generated for each Feistel round. This ended steps 1 and 2. After that, we got a resultant ciphertext with a left half and a right half. We swapped the left and right halves of the ciphertext and performed the initial inverse permutation to get our result. There are two factors on which DES should be analyzed. Avalanche effect. A small change in plain text or the key should create a significant change in the ciphertext. For example, suppose our plain text is 11010101. We perform DES on it and get our ciphertext as 01001110. Now let's suppose we make a small change to our plain text by changing the last bit from a 1 to a 0. If we observe the resultant ciphertext now, it will turn out to be completely different. As we can see, making a small change in our plain text caused a huge change in the ciphertext. Hence DES satisfies the avalanche effect. If we look at the completeness effect, each bit of the ciphertext needs to depend on many bits in the plain text. The confusion and diffusion produced by D boxes and S boxes in DS show a very strong completeness effect. Thanks for watching.